All right, hello everyone, and welcome back to another AP Physics C Mechanics for Response, I guess you could say walkthrough. Today we're going to do the 2023 set 1. So yeah, let's just get into it. Let's look at these questions. Okay, this one looks scary, but I promise you guys it's not that bad. Actually, it is that bad. No, I'm kidding. So a block sitting on a horizontal surface is pushed against the spring. Spring P, oh, see, this is what, okay, spring P. That is attached to a wall compressing the block at distance x. I'm going to keep that in mind. As shown in figure 1, the block is then released from rest. The block slides along the horizontal surface and up the ramp, okay, reaching a maximum height h max p. Frictional forces between the block and all surfaces are negligible. Okay, a student compares h max for spring P with the maximum height h max Q achieved with a different spring. Spring Q. Each spring exerts a force of magnitude F on the block that varies as a function of the distance x that the spring is compressed, as shown in figure 2. For spring P, Fp of x is equal to Kx, so just our regular Hooke's law, where K is 100 Newton meters. And for spring Q, F of Q of x, or Fq of x, is equal to Cx to the 1/2, where C is 20 Newton meters to the 1/2. Let's keep that in mind. So here's our graphs between the two. Okay. So we have both F and P, or both P and Q. For the experiment, the block is pushed against one of the springs, compressing the spring at distance x equals 0.001, or yeah, 0.01 meters. The block is then released from rest. In trial 1, spring P is used, and in trial 2, spring Q is used. And the following dots representing the blocks in trials 1 and 2 draw and label the forces that are exerted on each block at the instant the block is released. Okay, each force must be, okay, so that's just draw our free body diagram. So when the spring is really compressed, there's going to be the spring force on each block. We're going to start with spring P. Spring P, it's going to have the spring force. Oh, the length of the vertical vectors should represent the relative magnitude of the vertical forces. Okay, so what we need to do in this instance is recognize that when they're saying this here, they're saying they want us to respect the magnitude and make sure that like these grid lines will be accurate for both of these. So we're gonna look at well, I'll explain that in a second, but we're gonna look at the blocks. So in both situations, the blocks will be the same, so they'll have the same force gravity. So that means these two force gravities on both of these blocks should be the same length. Right? That means if gravity is the same, then the normal force also has to be of the same length. You can't leave one without the other unless you're on an incline, right? Okay, now we're gonna look at the springs themselves, right? So for that, we're just gonna reference the graph. That's why they gave it to us. So here's 0.01. So let's see, spring Q obviously has more force at 0.1. So we're gonna make that one go it looks like about double, about double. So we're gonna make this one go stretch all the way out to, oh my gosh, stretch all the way out to 4, but we're gonna make this one stretch only to 2. So we're gonna say Fp, as in the spring force from P, and Fu. So the reason I did this one to be 2 times longer than this one, like I said earlier, is we're gonna look at the graph. Here's like about 1, right? That's for spring P. Here's about 2, right? 2 divided by 1 is 2, so it's gonna be 2 times as big. And yeah. So the force vector would be 2 times as big because the force magnitude is 2 times as big. All right, let's see. B, what features of the graph on figure 2, so this figure, okay, could be used to estimate the work done on the block by each, oh, okay, so it could be used to estimate the work done on the block by each spring as each spring is compressed. So they're basically testing this idea that F times dx from A to B is equal to work. And they want to know, do you know what the integral is? And we do. So we're going to say the area under the graph. Graphs estimates the work. work by the integral definition. So this last part is just extra, but I like writing it. Right, so because work is the integral force with respect to distance, the area under a force x graph will give us work. Next question. So there's one compression. Oh my gosh, my handwriting's so big. I'm gonna lower this a little bit so you guys can see better. There is one compression distance x naught for which the maximum height h max reached by the block is the same regardless of which spring P or spring Q is used. Okay. So predict whether the value of x naught is greater than, less than, or equal to 0.04 meters. So let's look at where 0.4 is. It's right here where they intersect. Oh my gosh, I turned that off. So yeah, that's where they intersect, right? So I guess what they're basically testing is like, let's visualize this here. Here's our ramp. I'll erase this in a bit. So what we have to think is that the work done to compress the spring will equal the work coming out, right? Or well, you could think of it as this way. So because if I compress it this distance from 0 to 0.4, the force that the spring is going to push back on, the area under this graph is the work that the spring will do going back from 0.4 to 0, right? So essentially we're allowed to equate the work done to compress the spring and the work done and the work that the spring will do in order to push I guess the block back. And by the work energy theorem, we can say since work equals the change in kinetic energy, right? We're going to say that when the area, well, I guess when the work done, we're going to say work done by, oops, excuse that, done by both springs on the same blocks are equal, the delta K of the block are also equal. Therefore, K finals would be equal. And by E final equals E initial, UG finals would be equal. And therefore H max would be equal. And then we're going to say for all, this is the for all simple, I just read it like for all x equal to, we're going to say less than or equal to 0.04, the areas slash work are not equal. And that is true because if we look up here, right, this will always have this little edge up on this triangle, which is the other graph. Let me just erase this so we can see it better, right? So, because the area under the graph at this moment, why did it do that? At this moment will always be this triangle, right? But the spring Q graph will always have this little section like as a one up on it. So it has to occur later at like here-ish. I'm gonna say here-ish. There, I guess you could say, or maybe even further than that, there is when the works would be equal. So it has to occur after. Therefore, x naught occurs, excuse my handwriting, guys, occurs after 0.04 meters. So there's a reasoning for that. If anyone has any questions, feel free to ask them. But I think I explained it all right. Let's do the next question. On the axis provided for both spring P and spring Q, sketch a graph of the maximum height reached by the block as a function of the distance each spring is compressed. So maximum height is function of distance, ranging from 0 to 0.1 meters. Clearly label the curve for spring P and spring Q. This question specifically is the hardest graphing question I believe Physics C has ever asked. I've never had any trouble with any other one besides this question. But when you look at it, it's a lot easier. So we have to think, right? So we know both of the spring forces. The spring force for P was, I believe, a linear force. Okay, so we're going to, Fp of x was 100x, but Fq of x was 20x to the 1/2. So like we stated here, right here, like we stated right here, we can basically integrate work or integrate force to get work. And then since work is the change in kinetic energy, the work will give us the change in kinetic energy will have the same final kinetic energy, meaning we'll have the same final gravitational potential energy. We can basically say that the work x graph is pretty much the H max. It's my handwriting. It's pretty much the H max X graph. It's a lot of rough estimates with this class. So on Desmos, we're actually going to take a look at that. So just taking the integral intuitively of 100x, I know it's going to be 50x squared. I have Spanish keyboard on. 50x squared. And we're going to look at this. Okay, and now we're going to take the integral of 20x to the 1/2, which is 20x raised to the 3 over 2, all divided by 3 over 2. And we're going to look at these two graphs. So let's see, they're both concave up. That's important, right? So both of our graphs here have to be concave up. So we're gonna think about it. They have to intersect at some point, right? But it told us here earlier, the compression distance x naught is where they will intersect, right? So we're basically gonna say, okay, they can't, from here to here, no intersecting, because we just stated that. So we have to give our rough estimate of where they'll intersect. So I said somewhere like here, right? So we're gonna say after 0.6, they're gonna intersect. So I'm just gonna mark that on our graph. So here-ish, they're gonna intersect. So we're basically gonna sketch our curve. Which work will stay above the other work the entire time? And I know that's gonna be spring Q up until that 0.6 graph. So our FQX, let's just isolate that. All right, this is our FQ, right? So it looks kind of like, we're gonna say Q is this dotted line, and P is this, that was a really bad P, and P is this solid line. So we're gonna dot our Q. We're gonna just make it concave up, just like that. That's fine. They don't want more than that. Now our next one, it's also gonna be concave up. It doesn't matter if you think about like the order of the polynomials. No, they don't care. They just want to know there's points for concave up, intersection, and one being above the other. So we know that since this one was the linear force, it's gonna be less. Oh, it's gonna have less up until that intersection point. Yeah, I'm doing this wrong. Up until intersection point, and then it's going to start to pass it, right? Okay, and there we can just leave it like that, and that's our answer. So now let's do this question. So, oh wow, this is a long question. Okay, spring Q is attached to the wall and is at equilibrium as shown in figure 3. Block, so much hair. Block A has a mass of 0.12 kilograms, so I'm going to write that there. And block B has a mass of 0.07 kg. Block A is held at rest at the top of the ramp, and block B is held at rest on the bottom surface. Student releases block A, and as it moves down the ramp, and collides with block B. Oh, and it moves down the ramp and collides with block B. Okay, so the change in vertical height. Oh, great, they give it to us, is 0.75 meters. After the collision, the blocks stick together. That's important. Stick together and move to the right, compressing the spring. Frictional forces between blocks and all surfaces are negligible. Done. Okay. So let's think about it. It says calculate the velocity of the two-block system immediately after the collision between block A and B. So there's two elements of this problem. We're going to have to think about the change in velocity of block A, right? Because it gets some velocity from changing its gravitational potential into kinetic down here, right? Into kinetic because it's at gravitational potential equals 0. And then we're going to have to think about the change in velocity from the collision, right? Because from the change in momentum, well, not change, sorry, there's no change in momentum. Momentum's conserved because when it says stick together in elastic collision, momentum is conserved. We're going to have to think about the change in velocity thanks to the collision, right? So whenever you think collision, whenever you see collision, think momentum, right? So we're going to start off with finding the final velocity of block A as it falls down. We're going to call that V. Right, so we're going to start our conservation of energy equation. E final equals E initial. So what's the initial energy of the block? Well, block A has its mass of block A, gravitational constant, mgh, is equal to, okay, the final kinetic energy. So 1/2 mass velocity squared. Oh, well, I see maths on both sides. I'm going to cancel. This is just the general equation you can memorize, but this is the velocity. Now we're going to plug in our numbers to 9.81. Gravity is a constant. The height they gave us was 0.75. And we're going to put that in Desmos. Square root 2, 9.81 times 0.07. Was it? Oh, it's 0.75. Okay. And that should give us, let's see, velocity, which will equate to 3.83601 meters per second. Great. So we'll leave that there. We're not done yet. So that's we're going to call that V naught. Now we're going to do the momentum part of this problem. So we're going to think, since it's an inelastic collision, the final momentum has to equal the initial momentum. So the initial momentum was the mass of block A and its initial velocity. That initial velocity being this one that we just calculated. The velocity it has as it comes off the ramp before it collides. And then since they stick together, we're going to add their masses, MA plus MB, V final, right? So now we know MA and MB, and we know these two values. So we're going to solve for V final by just moving constants on moving our values that we don't need on the other side. And now we can plug everything in to find V final. So V final equals, so the mass of block A was 0.12 kilograms. And then the velocity that we calculated was 3.83601. Now we're going to divide. So it was 0.12, the mass of block A, plus 0.07. And that should give us the final velocity. So we're going to go ahead and do that. 0.12 times 3.83601 divided by 0.12 plus 0.07. And that gives us a final velocity, I'm going to put it up here, of 2.4227 meters per second. And you can leave that as your final answer. That is the final answer. And yeah, that's all this question wanted because it says immediately after the collision, we can stop there. So now it says calculate the maximum compression of the spring. Now, normally you might be thinking, okay, well, I would do conservation of energy. You can absolutely do that, right? Because we know the spring used is spring Q. There's multiple ways to do it. I can go through both, but I'll go through the one College Board does just really quickly. What you could do is F equals negative du dx, and since you were given the earlier equation of cx to the 1/2, all you have to do is integrate the force, the negative integral of force, to find the potential energy as a function of x, right? And then you can use conservation of energy. I won't be doing that. I'm going to use the work energy theorem and take the spring out of the system by saying the spring force does work on the block to change its kinetic energy. So there's two approaches. There's spring potential energy. You just have to derive the equation because it's a nonlinear spring. So it's not 1/2 kx squared. No, it's a different equation, right? Because it's cx to the 1/2, not cx. So I'm going to take the spring out of the system and say the work that the spring force does. That's a really bad W. I can't live with that W. The work that the spring force does has to equal change in kinetic energy of the two blocks. So we're going to go ahead and start. Well, our work is non-constant, right? Well, sorry, our spring force is non-constant. So we're going to have to integrate for work. Oops. So we're going to go from where the spring force is 0, right? Where the compression is 0 to where the compression is at its maximum, right? Because from here to here, maybe I should just use the diagram. From here to here, x equals 0 to, well, we'll just say like x compressed. This would be the distance that work is being done. So we can write it like that, and our variable will go in there, and it'll come out later. And the spring force was C, where C is 20, so we're going to take our 20 out. X to the 1/2 dx is equal to, and delta K is 1/2, and the mass of A, mass of B, because they stuck together, they're moving as a system, delta V squared, right? And when I say delta V squared, I'll show you in a second, it'll come out later. So just really quick, I'm gonna make this easier on ourselves, and we're gonna combine like term, or what we're gonna move terms to the other side. So now we're gonna divide by 20, we're gonna get divided by 40. And delta V squared is V final squared minus V initial squared, right? And this spring is actually doing negative work. I forgot that earlier, but the spring is doing negative work because the spring force is that way, but the displacement is this way. So cosine of 180 degrees is -1. So the spring is doing negative work, right? Because the force vector and the displacement vector are in opposite directions. So we'll leave that negative in there. So I'm going to simplify this integral. So the integral of x to the 1/2 is going to give us x to the 3/2 divided by 3/2 from the limits of 0 to x compressed. And we're going to make that negative. And then we're going to put the equals to here. So that negative, I'm just going to multiply on by both sides. Well, it'll come out in a second. I'm going to simplify this side because the final velocity, when it comes instantaneously to rest, when a spring is at its maximum compression, anything attached to it comes instantaneously to rest. So when it's instantaneously at rest, the velocity is 0. And now I have a negative here, right? That'll factor into this equation and make that entire thing negative. Well, I'm just going to cancel those because I don't want a negative distance, and we can leave it like that. So now this 3/2, I'm going to simplify. I'm going to simplify this over here. So x compressed to the 3/2. Now I'm going to move that 2 up top and do this. Right? This 2 and 3 came from me multiplying 2 on both sides and simplifying. And now if I'm going to put 0 in this numerator, it's just going to be -0. So we're just going to ignore that. Is going to equal MA plus MB divided by 40. That negative canceled earlier times the initial velocity squared. Right? So now I'm going to simplify, and it's going to be a really big and ugly equation, but it's okay. So we're going to do 3/2. We're going to move that 3/2 to the other side, times MA plus MB divided by 40 times the initial velocity squared. And we're going to raise that entire thing in order to get to the 3/2 here. We're going to raise that to the 2/3, so it'll cancel out to 1. If we raise one side to the 2/3, we have to do the same thing to the other one. Is going to give us our compression distance. Now I'm going to plug in all my values. So 3/2. So the mass of A was 0.12 plus 0.7, not 0.7, 0.07 divided by 40. And that initial velocity that we got earlier was here, 2.4227. That's why they made us do that problem before. Sorry, I'm running out of space, guys. And that's squared. And this entire, oh my gosh. Ugh, ugh. This entire thing is going to be raised to the 2/3. So I'll just put it on Desmos. Maybe it's easier to see there because I ran out of space here. So we'll do that. 0.12 plus 0.07. Divide that whole thing by 40. Now we're going to multiply by 2.4227. Remember, that's the initial velocity after the collision had happened, but before the spring was compressed. raised to the 2/3 should give us our answer, which I believe to be correct. Yeah. 0. So our compression distance is roughly 0.12 meters. And that's how you solve that problem. Again, there's the alternate approach where you could derive a potential energy function. You don't need to do that. But yeah, so this question's taking a little while. It normally would take 15 minutes, but I'm just going through everything and explaining it. But yeah, so spring D, where FQ of x is equal to Cx to the 1/2, is replaced by a different nonlinear spring, spring R. Oh, okay. And the procedure described in part D is repeated. So now these guys have the same functional dependency. So it's x to the 1/2. So for spring R, this is the equation. The maximum compression, so the maximum compression of spring R is greater than the maximum compression of spring Q. Okay, so it's saying this scenario is repeated. Now this is going to be replaced with R, and spring R is going to compress more than spring Q. So it's going to ask about the constants. And now what I'm going to say right here is that D is less than C, or C is greater than D. Now the reason for being is because both scenarios have same initial V before before hitting the springs, and hence same initial K. Kinetic energy, right? Work equals delta K. Work, K final, and K initial are same. Therefore, delta K is same. Therefore, work is same. Slash constant. I should put the is the same. There we go. So work is the same slash constant, right? More compression requires less constant, or well, I guess spring constant to maintain work constant, as work equals, we're going to say integral K x 1/2. Oh, that's bad. 1/2 dx. Therefore, C is greater than D, right? So because the spring C, or because spring Q compressed less, its spring constant must have been greater because it can supply the same force to change the kinetic energy with less distance. But since this one needed more distance, that means its spring constant must have been weaker, right? Because if one goes up, the other has to go down. All right, next question. A student makes a torsional pendulum by suspending a uniform disk of mass. Oh, this is simple harmonic motion. Okay. Makes a torsional pendulum by suspending a uniform disk of mass m and radius r from a light wire with a torsion constant kappa attached to the center of the disk as shown in figure 1. The rotational inertia of the disk is given by 1/2 mr squared. The student conducts an investigation to determine the relationship between the period of oscillation of a torsional pendulum and the number of identical disks that are suspended from the wire. The student starts with a single disk, holding the disk a small initial angular displacement theta naught. From the untwisted position, the student releases the disk from rest and the pendulum oscillates. The student records the period of oscillation for a single disk and an additional identical disk. So he's going to repeat the entire thing for n equals 2 disks through n equals 10. Assume the disks move together as one system. So it says using t equals 2 pi I over kappa. Okay, derive an expression for t as a function of n. Okay, so they want us to use these constants. So what we need to recognize what is changing. The torsion constant is a constant. 2 pi is a constant. So the moment of inertia is the only thing that can be changing. So each disk has mass m, right? So the mass as a function of n will be nm. So the moment of inertia as a function of n will be 1/2 nm r squared. So now we're going to plug that into the period equation. So we're going to say t equals 2 pi square root nm r squared over 2k, or 2 cap. And that's it. That's literally it. That's all you have to do. Because as you add more disks, the moment of inertia will change as you're just increasing this mass linearly. And then you just plug that into the period equation. You can leave it like that. If you have any other questions, feel free to ask them in the comments. Because I went over this one a little bit quicker, but it's a quick problem. So the potential energy stored in the torsional pendulum when the disks are displaced is U equals 1/2 kappa delta theta squared. On the following axis, sketch the maximum kinetic energy of the torsional pendulum as a function of n, where n is greater than 1. So this question, basically, we need to realize that in simple harmonic motion, energy is conserved. So as this, I should draw this better, as the disk will twist a distance theta away, it'll come through the middle and have its maximum kinetic energy as it's passing its equilibrium. But its maximum kinetic energy, sure, it's dependent on mass because it's 1/2 mv, or 1/2 iw squared, right? And I, moment of inertia, is dependent on mass. But all we need to realize here is that kappa is not changing. Delta theta is not changing, right? This is a constant. And you may be saying, well, hey, wait, the mass is changing. You're absolutely right. The mass is changing for n is greater. So if the mass goes up, the angular velocity will decrease. The kinetic energy will stay the same because conservation of energy, E final has to equal, oh, that's not a vector. E final has to equal E initial. This initial energy cannot be created or destroyed. So the angular velocity will just decrease in order to account for the mass's increase. The kinetic energy will have to stay the same because this potential energy was a constant. So that's our graph. All right, next question. The student plots data for t as a function of square root n as shown. So we're going to just write that equation that we derived earlier because it'll come in handy. I think it was square root 2 pi nmr squared. nmr squared over 2 kappa. Okay, we'll leave that there. So it says draw a line of best fit for the data. I'm going to use this. Let's see if I can do it. Because I honestly suck at graphing, but it's okay. We'll try. So my line of best fit might be a little bit different from yours. But there's my line of best fit. All right. So the student previously determined that the radius of a disk is 0.2 meters and that kappa is 1.6 Newton meters. Using the graph, calculate the mass m of a single disk. So this is a linearization problem. What we need to do is rewrite this equation that we were given. We're going to write it in the form of y equals mx plus b, or plus b. And there's no plus in this equation, so it's just y equals in this equation. So there's no there's no plus b. So I'm going to take out square root n from everything else. So it's going to become mr squared over 2 kappa, and then root n. And we're going to realize this is my y. This entire thing is my m, and this is my x, right? So we're going to say, since our m is our slope, we're going to pull our slope from our graph, but we have to make that statement. Slope is equal to the change in period over the change in the root of n, which is also equal to 2 pi. Right, College Board gives you a point for writing this statement. I like to write it on all of my exams just to make sure I don't miss it. 2 kappa. So that's our slope, and we're also going to pull our points from the graph and make another equal sign. So I'm going to pull one. So, okay, that's close enough. So that's 0 0.123, 0.3, comma 0.1. We're going to look close. I like to always pick polar opposite points, right? So here's 2.7. That's like, oh, so 2.7, and that's 0.7, and that would be 0.75, so 0.725. So those are my points, and I'm going to calculate my slope. So change in y over change in x, so it's going to be 0.725 minus 0.1 over 0. Oh, was my x? It was 2.7 minus 0.3. Let's do that in Desmos. 725 minus 0.1 divided by 2.7 minus 0.3. Great. And that gives us roughly 0.26041. And now we're going to do our calculations. We're going to solve knowing that slope is equal to this big thing here. We're going to just move the terms over so we can solve for m. So divide by 2 pi. Square that whole thing. We're going to multiply by 2k and divide by r squared. And that's going to give us m by itself. And you may be asking, well, how did you get there? I'm going to start doing it over here. So we're going to say, I'm going to call slope s, just for simplicity. Square mr squared over 2k, right? We divide by 2 pi on both sides to cancel it, right? Now that equals mr squared over 2k. Forgive my handwriting. Now in order to get rid of that square root, to solve for m, we're going to square that. Now we get mr squared over 2k. 2k is on the bottom. We're going to multiply by both sides to get it by itself, right? And then we would divide by r squared. That's up here, and that's how we got that, right? So that's all you need to do. So I'm just going to leave that like that. And then I'm going to plug in my values, right? So we're going to take, what was our slope? 0.26041, yeah, divided by 2 pi. I'm going to square that entire expression. The torsion constant, they gave it to us. It was 1.6 Newton meters. 2 times 1.6 divided by, what was r? 0.2. That's going to be squared. We're going to put this in Desmos, and we're going to let Desmos do the heavy lifting for us. That's 4241, 2 pi. Square that entire expression. 2 times 1.6. Divide, we're going to have to divide the whole thing. It's the same thing. Divided by 0.2 squared. So the mass is roughly 0.13741 kilograms. And that's your answer. All right, next question. The student finds that the value given by the manufacturer of the disc is less than the value determined experimentally in part CII. Determine a single source of experimental error that could result in the observed difference in the value of m. Okay. So a single source of experimental error that could result in this, we just have to realize, okay, sorry, it says the mass of the disk is less than what it was. So how does slope relate to mass? We have to think about it. Because the slope was on the top side of the equation. So it's directly proportional to mass. So what could have changed slope? We could say, we'll think about the moment of inertia of the disk. We'll think about the mass of the disk could have been concentrated at the edge, increasing I, which is the moment of inertia, increasing I, and because it would increase slope, increasing slope as slope is proportional to the square root of I, and that's from this equation up here, right? And if you may be thinking, well, the n is not there. It is, because this is this is the moment of inertia, right? Just by itself. The n is just a part of a constant. We can just pull the moment of inertia from here, say that's I, and then say that it's proportional to the slope. So increasing slope, as slope is proportional to I, increasing mass. Done. And that is the exact question that they're about to ask here. The student repeats the experiment, but now the disks have a density that varies as a function of the disk according to rho equals 0.3 r. With the slope of this best fit line, it's going to be greater than. So we're going to say slope is proportional to the square root of I. Higher I as density is non-uniform, therefore higher slope. And that's all they want for this question, really. So when n equals 1, the maximum angular speed of the torsional pendulum of a uniform disk is found to be Wu. When n equals 1, the maximum angular speed of the torsional pendulum with a non-uniform disk is W non-U, which correctly compares the W of the the W of the uniform disk and the W of the non-uniform disk. I'm going to say this one, and we're going to say since E final, it's not a vector. That's the equal E initial. K rotational has to equal U. We'll bring that over here. We'll say our rotational kinetic energy has to equal 1/2 kappa theta squared. 1/2 kappa theta squared is a constant. Non-uniform disks have higher I's than uniform disk. If I is higher, W must decrease to keep K rut constant. Therefore, WU is greater than W non-U. And I should have just put, since K is constant, therefore K rot is a constant. You get the idea though, that's this constant. All right, next question. And if you have any questions on that, please, in the comments, I'd love to answer them. So a system consists of a small sphere of mass m and radius r at rest on the horizontal surface, and a uniform rod of mass m equals 2m and length l attached to one end of a pivot with negligible friction. Okay, so here's the rod. So the rod has 2m, this has m, and this has r. And this has L, where R is super, super smaller than L, so it's negligible. Okay, there's negligible friction between the surface and the sphere to the right of point A, and non-negligible friction to the left of point A. So here, there's no friction, it doesn't matter. Here's mu, right? The rod is held horizontally, shown in figure 1, and then is released from rest. The total rotational inertia of a rod about the pivot is that. The rotational inertia of the sphere about its center is that. After the rod is released, the rod swings down and strikes the sphere head-on. As a result of this collision, the rod is stopped. Great. Perfect. And the ball initially slides without rotating to the left across the horizontal surface. Derive an expression for the angular speed of the rod striking the sphere in terms of L and physical constants as is appropriate. So this is the rotational equivalent of a mass sliding down an incline, right? It's conservation of energy. Excuse me, I'm just stretching. So conservation of energy. So we're going to have to say E final. There's no vector there. Equals E initial. So we're going to do this about the center of mass because that's where gravity acts. So the center of mass height, it's going to switch from this to this. Center of mass height will be L over 2, not L, not L, right? Because the center of mass doesn't go all the way down here. No, it doesn't. That would require you to shift the bar down. No, it just swings 90 degrees and hits L over 2. Because if I draw this like here and then I draw this vertically, here's the center of mass, here's the center of mass, it's at the middle. Well, the center of mass drop the height of L over 2. We're going to assume this to be our 0. It's arbitrary point. That's how you pick it. And we're going to assume that this change in height is L over 2, not L, not L. So we're going to say the mass of that rod was, I think, 2m. Yeah, 2m g L over 2 has to equal the rotational kinetic energy. I should probably just make this statement. I'll make the statement. UG goes to K rotational, goes to the rotational kinetic energy, 1/2 the moment of inertia of the rod, the angular velocity squared, right? So now I see over 2, I see 1/2 on both sides. I'm going to cancel that, right? 2mgl equals, and the moment of inertia of the rod about the pivot is 1/2 big M L squared. So earlier I subbed in big M for 2m here, right? I'm going to do the same thing with the moment of inertia, 1/3 2m L squared W squared. I see 2m on both sides. Cancel, cancel. I'm going to multiply by 3 on both sides in order to get that, in order to simplify the expression. So now I get 3g, excuse me if this is messy, 3gl is equal to L squared, W squared. I'm going to divide by L squared to get W by itself. 3g divided by L equals W squared, square root to get W by itself. And our final answer is square root 3g over L equals W. So there's our answer, right? All right, next question. Derive an expression for the linear speed v naught in terms of the sphere immediately after colliding with a rod in terms of length, in terms of the length L and physical constants as appropriate. So this question's also a little bit quick. I'm going to go through it. Conservation of angular momentum. So the reason why we're doing that is because we need to recognize there's no net external torque on this system, right? So angular momentum will be conserved. So we can just leave it like that. So the initial angular momentum is IW because it's in the form of the rod swinging, right? But the final angular momentum will be in the form of this, about this pivot. So that's because you may be asking, yeah, how can something that has like regular velocity have angular momentum? It just does. That's how physics works. It's really nice though. It turns out really nicely that we can do that. So we're gonna say R cross P, right? So I of that what's it called? Of that bar was 1/3 2m L squared and the square root of 3g over L. We're subbing in our answer from over here, from up there, right? And has to equal that radius, that R is going to be this R, right? So R would be L. And L, and then it's going to say M, the mass, what was it? It was M, and then V final. We're going to call it V naught. So MV naught L, right? So now we're going to simplify. This is going to be annoying, but we're going to simplify. So it's 2/3 ML square root 3. Oh, that M is on both sides. We're going to cancel that. I'm going to take that out of my answer. I'm just going to delete all that. 2/3, because it's on both sides. L squared. Oh, it's just one L because I'm dividing by L here in order to cancel that. Square root 3g over L equals V naught. I could leave it like that. I'm not going to. I'm going to take that L and put it inside the square root. And that's our final answer. I put it inside the square root by just saying, okay, L squared. Well, this would be that, so I could just remove that. And then L squared divided by L just gives me L. So that's our final answer, and we can leave that like that. And you may be seeing something on College Board's website for the answer that's more simplified. This is the same answer, I assure you. So after sliding a short distance, at time t equals 0, the sphere encounters a region of the horizontal surface with a coefficient of kinetic friction mu, beginning at point A as indicated in figure 1. Okay, the sphere begins rotating while sliding and eventually begins rolling without sliding at point B. So here it's rotating while sliding. So like a bowling ball, it's like, uh, uh. And then here it's perfect. It's the ideal case. It's rolling without slipping after B. So in the following diagram, which represents the sphere while it's traveling between A and B. So it's rolling without sliding. Draw and label the forces, not the components that act on the sphere. Okay, so this is a force body diagram. So it says each force must be represented by a distinct arrow starting on the point of contact. So we're gonna do this. So gravity always acts at the center of mass, right? The normal force acts from the point of contact, and friction opposes the direction of motion. At least it should. Friction, is it? I believe it to be, yeah, it's that way. Because the mass is this way, friction goes that way. I'm gonna call that FF. Or F. It's so much easier to work with that way. Okay. Derive an expression for each of the following as the sphere is rotating and sliding between points A and B in terms of V naught, mu, R, T, and physical constants as appropriate. The linear velocity V of the center of mass is a function of time T. There's two ways to do this. See function of time, you might be thinking differential equation. We're not doing that. You could do that. Go ahead and look at College Board's website. They walk through it. It's really easy. But we're going to use kinematics here. So we're going to derive. We need to understand that as it's sliding here, it has a constant acceleration. Constant acceleration backward that causes it to. Well, let's look at the force body diagram. It's not accelerating up or down. Friction is the only thing that causes the acceleration in the x direction. So we're going to say sum of forces x equals the force of friction, which is equal to max. We're going to look at the y now in order to get mu Fn, because friction is equal to mu Fn, right? Sum forces y equals force normal minus force gravity. I'm sure you've seen this 100 times. Force gravity equals force normal. Therefore, force normal equals mg. Now I can sub this in for mu mg equals max. This is a lot of equal signs. This is like how I show my train of thought, though. So now if mu mg equals max, put that negative there. Sorry, friction is in the negative direction because I'm going to define my positive where the initial velocity is, and my negative is going to be that way. Because friction's negative, I'm going to say the acceleration on the x is negative mu g. Going to use kinematics. V final equals V initial plus AT, right? Well, V of t essentially would be, what's that V naught that did they let us use? They let us use V naught, is V naught minus mu gt. So that acceleration turned into a negative because friction is slowing down. So friction opposes the initial velocity that's this way because the acceleration is that way, so it has to slow down. So here's our answer. You can leave it like that. The angular velocity w of the sphere is a function of time. Again, you can use a differential equation. I'm not going to. We're going to do sum torques equals I angular acceleration and recognize that the friction provides a constant torque that I'm going to call tau of F. Right? I'm going to simplify this right side down. We know it was 2/5 mr squared, and you may be asking, where'd you get that? Up here. This is where they give it to us, right? So that's the rotational inertia of the sphere times angular acceleration has to equal, well, torque is radius cross force. And we said that the radius of the sphere, well, the radius of the sphere is just its own radius. Friction is mu mg, as we said earlier, right? Oop, right? And sine, the sine between the two angles, friction's at 90 degrees. It's sine 90. That's one. We can ignore it. We're going to simplify it to find angular acceleration. So this r is going to go to the, we're going to divide by r squared. And everything else, this will become, we'll cancel m on both sides. It'll become mu g, right? 5/2 r equals angular acceleration. Great. That's our angular acceleration. We're going to use angular kinematics. We're going to say W final equals W initial plus angular acceleration t. And our W initial is 0, right? Because it's not sliding. Yeah, it's not it didn't have any initial angular velocity. So we're going to say W of t is equal to 5 over 2 mu g t over 2 over r. And that's our answer. And you may be asking, this is a commonly asked question. Why isn't this negative? Why is that not negative? The reason for friction not being negative in this instance is because we're going to pick our direction of acceleration to be the positive direction for rotation. So even though friction is applying a clockwise torque, right, because radius cross force, which would give us a negative torque, I'm picking that to be my arbitrary direction, which would be positive, right? It comes in later, but you cannot say that the angular velocity will be decreasing because it's actually increasing, right? It won't get increasingly negative. You could just pay respect to the direction, but it will be, you could say it's negative, right? And say that the direction is the negative, but in this essence, we're going to think of it as positive because it's going to be increasing. Always pick your direction of acceleration to be your positive, unless you have an initial velocity that is positive. In that case, pick that to be your positive and then go based off that. That's what I did up here. So now we're going to go to these last two questions and then we'll be done. So derive an expression for the time it takes for the sphere to travel from point A to point B in terms of V naught, mu, and physical constants as appropriate. So this is where that positive thing comes in. This is why I picked my direction of acceleration to be positive, and I always like doing that. It's so much easier to do that. It's like you should always stick to that, but especially with these problems, because if you don't, then your answer comes out wrong. Well, actually, it's arbitrary, but you'll have to tweak it a little bit. I'll show you. So in terms of V naught, mu, and physical constants is appropriate. So the condition for the sphere to travel from point A to point B, we have to recognize that earlier it said to us at point B, it begins to roll without sliding. The condition for rolling without sliding is V equals RW. Whenever you see like how long does it take for it, you think this. You think this equation. So we derived V of t. We want to see when will V of t equal R times W of t, right? So we'll just sub in our equations and plug in for those. So we know V of t was negative V naught minus mu gt, which is equal to R times 5 over 2 R over mu gt. Well, I see R on top and bottom, so I'm going to cancel that. And now I'm going to take this up here. I'm going to say V naught equals, I'm going to actually add mu gt to both sides because I have like terms. 5 over 2 mu gt plus 2 over 2. Well, you may be asking, where's the 2 over 2? This is 1 over 1. I just said it's 2 over 2 because 2 divided by 2 is 1 mu gt. And that'll give V naught to be, oh, sorry, that'll give us this 7 over 2 mu gt, but they ask for time, right? So we're going to simplify. We're going to say 2 V naught divided by 7, oh, not V naught, 7 mu g equals t. That's our time. We can leave it like that, right? Now it's going to ask us, derive an expression for the linear velocity of the sphere upon reaching point B in terms of V naught. Okay, so all we need to do is plug in that time into this equation. So our time, this is our time, equals V final, right? So our time that we got was 2 V naught over 7 mu g. So I see mu g on top and bottom, so I'm going to cancel those. Now it becomes V naught minus 2 V naught over 7 equals V final. Well, 1 over 1 is 7 over 7, so 7 over 7 V naught minus 2 over 7 V naught equals V final. That means 5/7 V naught equals my final velocity. And yep, that's the end of the exam. So there's another exam. That's the 2023 Set 1 AP Physics C for your response. We'll be doing the Set 2 probably today or maybe another day. Um, But yeah, I hope you guys enjoyed the video and learned a lot from it. If you have any questions, please go ahead and put them in the comments. I'd be delighted to answer them. And I wish you guys luck on all your exams. Yeah, I'll see you guys in the next video.